So now we'll see the second video on Karnaugh Map, which is K map, and a visual way to simplify logical expression. We use this K map, and it also gives the most simplified form of Boolean expressions. A K map is a graphical method used to obtain the most simplified form of an given Boolean expression. So the standard form we use here is sum of products or product of sums. The simplest form of an expression is the one that has the minimum number of terms with the least number of literals, that is the variables here. And by simplifying an expression to the one that uses the minimum number of terms, we ensure that the function will be implemented with number of gates. So as you see here, we have this three variable k map denotions here. So we'll see to the first f is equal to the given function, that is the Boolean expression given as f is equal to summation of 0 and 4, and which is equal to b dash comma c dash into c dash. So here the 0 and 4 in the summation function has been taken as the min terms here. So we'll given that we have three variables, so a, b, c are the three variables denotion taken, and in 0 and 4 position of the squares we will be placing denoting denotion ones, and this is again grouped, and the as we see here the expression is a dash b dash c, and a b dash c dash. So here b dash and c dash will be taken into as a common term. As we see here, a dash plus a will be left out in resolving it. So as the simplified Boolean theorem and the equation, a dash plus a is equal to 1. So we'll get the product as b dash c. So this will be your function simplified Boolean expression. So likewise the similar examples have been discussed here. So here K-map assessment have been given here, and four variable K-map also functions similar to the three variable K-map. So here we use three variables with 4 rows and 4 columns, as we discussed in the earlier videos. So here the cell adjacency here is discussed. So what are all the adjacent cells? As we see in the previous video, the adjacent cells have been grouped here. So how many types of grouping can be done has been shown here. So to the left, first image denotes the grouping of the adjacent cells in the second row, and in the second square we have the grouping of the adjacent cells in the third column, and in the third square we can see individual ones have been grouped. Since no adjacent ones is available, we take individual ones as grouped here, and to your fourth also the same concept of individual ones grouped here. So here second row first square we can see that adjacent columns are similar, and we are grouping the second and the third column into a single group. And similarly the next square we can see the column 1 and column 4 are adjacent, and we are grouping it to form a group. And in the next second row and the third row are adjacent, and we have ones in all the squares here, so we group them together. And similarly we have grouped the row 1 and row 4 since they are adjacent to each other. So likewise the cell adjacency can be grouped to simplify the Boolean expression. So the digital circuits and the combinational circuits can be designed using the input and output truth table, and we shall look into an example here. So the steps to design combinational logic are: from the problem statement, derive the truth table. First step is to form the truth table from the given expression. Second step is from the truth table derive the unsimplified logical expression. Then simplify the logical expression. From the simplified expression, draw the logic circuit. So here is the example: design a 3-input A, B, C digital circuit that will give as at its output X logic 1. only if the binary number formed at the input has more than zeros. So here we have been given with three inputs with an output x. So we can draw the logical diagram a, b, c, or the variables we'll take. So here we shall take the a, b, c, and we shall derive a truth table first step. So from 1 to 7 we are assigning the binary equivalent for the variables a, b, c. So as you see, the binary equivalent of 0 to 7 decimal value have been listed here, and here we have been given with the output. Okay, so when we okay, so here more than one binary value we should take output as 1. So more than one and both we have the binary equivalent of 3 have more than one denoted in its input. So the x comes as 1, and similarly in for the 5 binary equivalent we have two ones in the binary equivalent, so we are taking it as 1, and the output will be 1. And similarly for 6 and 7 we will be marking it as 1. So based on this we shall mark the ABC K map shall be done, and the K map using the K map we shall derive a Boolean expression, and with that Boolean expression we are coming to a term that the Boolean expression gives you ABC, and we are using product and sum in between the expressions. So the product is done and then the sum is taken. So first we will use an AND gate and followed by the OR gate to produce the X value. So this is the design to draw a combinational digital circuit. Thank you.